Thank
time
you.
is yours, dear Gleb.
Yes, so the title. So it's a joint work with V.Danilov and Alexander Karzanov. Yeah, okay. So in 1980, Alexander Zamolodchikov consider higher dimensional generalization of quantum Young-Baxter equation. And so what's now known as tetrahedron equation. So it looks as follows. So we just take some matrix in tensor product and endomorphism of tensor product 3 times V, and consider, we say that it is solution of the following equation. So if the following holds, so we just take 6 times V so it's 6 times, and then consider the following two maps, this tensor product to itself. So one is just defined A1 to 3, A1 to 4, A1 to, just 1 second. So it's 1 to 3, 1 to 4, 2, 4, 6, and 3, 5, 6. So that means that you just apply operator. So if they are indices, then you just apply operator to the three terms with this operator and identity outside. And then it has to be equal, written this in reverse order. And so he found a solution to such equation. And so it's not very, it's very non-trivial, because if dimension of V is n, then you have n in power 6 variables and n in power 12 equations. And then it was consider a generalization of this equation for d-simplex. So it's called d-simplex equation. So then you consider in endomorphism of tensor product d times. And then the equation would be the following. So you consider tensor product in the amount d on d plus 1 divided by 2 times. And the equation will be written as follows. So just rule is similar to this. I will explain this is for 4, not to make mistake, but then you will understand how to do this. So you have just, in general, to do 1, 2, so maybe 5. I will take d equal 5. So then you have just to put it for 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And now you have just to read this following. So you just first you take A1, 2, 3, 4, 5. Then you just take the dot here and you just write this hook. So then it would be 1, 6, 7, 8, 9. Then you take another. Then it would be A, 2, 6, 10, 11, 12. then the next one. So it would be A 3, 7, 10, 13, 14. Then it would be this one. And it would be A 4, 8, 11, 13, 15. And the last term would be just this column. It would be 5, 9, 12, 14, 15. And then you have just to write it vice versa. Then it will be a little bit complicated. So then there is also related to this story, this so-called set theoretical d-simplex equations. So they were invented by Buchstaber. And so then instead of consider tensor product and endomorphism, so one have to consider a map just from product of spaces to itself and just with same machinery. And for if we consider tetrahedron case, so then a nice solution which appears in theory of canonical basis is Lustig transformation. So if you just take map from C times C times C to which defined by the formula x, y, z goes to x plus z, yz divided on x plus z, and xy divided on x plus z. Then it's such a map satisfy, so it's would be set theoretical solution to this tetrahedron equation. And in 1986, Manin and Schechtman consider theory related to the higher Bruhat orders. Which generalize Bruhat order on symmetric group, and they do this in relation to this story, thinking about some combinatorics of this Zamolodchikov equation. And so, what would be the aim of the talk? So now we consider. So we just inspired by this combinatorics from Manin and Schechtman. So we just take a directed graph G. So we have a graph G. So it is a directed graph. Without oriented cycles. And then by such data, so we construct, so we have such a graph. We take a solution to d-simplex equation, and by this data we construct element dt of G R, which is in endomorphism of V tensor product of some number n which depend on the graph and D, or it is a map in the set of set theoretical and G of D. So this could be thought as a like Donaldson-Thomason transformation with respect to this graph and solution to Young-Baxter equation. Okay, so then I just consider here. So, in graph we consider, so we have directed graph, then a path P is collection of vertices such that, so if we consider pair of neighbors, then they are edge of our graph, and this calls this vertex is tail, and this is head. A pair of passes P and Q. So P is U0, UK, and Q is V0, VL. A pair of passes is called tandem. Is a tandem if UK is equal V0. So that means that we just can concatenate the two passes. And then concatenation is just the pass U0, UK, V1, VL. So let P of G be the set of passes in G. And then definition, a linear, so what is total transitive relation on P of G is convex if for any tandem so a linear order, so I will call it like this one, on any tandem PQ orders its free passes either P less than P concatenation Q less than Q, or Q less than P concatenated with Q and less than P. Okay.
What's the relation between G and R?
What?
What's the relation between G and R?
Where? Graph and solution. What relation?
So D is not a parameter of the graph.
D is not parameter, is a number.
An extra number.
Yes, so it's a, and G of D, it would be some number, which I will define. And motivation to call this order convex, it just come from root systems. So if we consider a line graph, example, so if G is line graph, so it's with 1, 2, etc. n, then passes in such graph, so a path is just the interval. So we just take from some vertex, we go to some vertex A, which is strictly smaller than G. We not consider trivial passes from I to I. And then such paths which started at I and ends at G correspond to positive root alpha J I, which is EJ minus EI in the root system for the SLN. And then the condition of concatenation is just that if we have two passes, they form a tandem. So if we just end it with G, and then we have just to start again from G. And that means that we have root alpha GI and root alpha KJ. And so therefore it's just that sum of these two roots is also a root. And then in this case, so this is convexity means that if we have positive roots, so we have just, then we order positive roots in such a way. So if we just found somewhere free roots such that it is alpha, alpha plus beta, and this is gamma, so then they always ordered like this and this. And this is things important for such orders to construction PBV basis in the quantum group related to SLN. And now we define definition a D Cartège and D more equal than 2 is a tuple of D passes P1, PD, such that Pi and Pi plus 1 is a tandem. So we just take a sequence of passes such that each two passes they can be connected. They form a tandem. That means that we had consider concatenation, and then it would be non-zero. So the set of D Cartèges is denoted by PD of G. Okay, so and now we associate to each D Cartège the following sequence. So if we have D Cartège P, then we consider the following sequence S of P, which is consists of the following elements. So it is S P1. It is so we just forget about the first pass. So then it would be P2, PD, and then SI P is equal P1 Pi concatenated with Pi plus 1. It's Pi minus 1 for I equal 1 D minus 1. Yes, and so maybe it's just I will change notation. Sorry, it will be minus 1 I plus 1 and I minus 2. Then it would be from 2 to D, and then the last element S D plus 1 P is just that we forget about the last pass here. Now we define So n. So now it would be n. I define this number ngd. It's just the number of d Cartesians in G. So this is this number which will appear. Now we define convex order on maybe d minus. Okay, so I will check later. So a linear order on p d minus 1 of G is convex if for any d Cartesian p. So just I have to notice trivial fact that this sequence is, so if we started from d Cartesian, then the sequence is consisted of d minus 1 Cartesians. So we just construct from d Cartesian a d plus 1, d minus 1 Cartesians. For any Cartesian, so either the sequence is ordered standard, so that means sd plus 1 p less than sd of p, so on, s2 of p, s1 of p, or anti-standard, s1p less than s2p. And then we would interested in studying such linear orders. And first, what we have to be sure that the set of such orders is non-empty. And then this proposition, the set of convex order on PD minus 1 of G, which is denoted O D, oh no, maybe it's a little early, yeah, okay, is non-empty. And just as a proof, so we can just in the proof, so this we can show that if we consider standard order such that for any d Cartesian, any sequence is ordered standard, is convex. That means that that it has to, we have to check that it's transitive and total, and also the anti-standard is also convex. So if we just order all such sequence in this way or this way, so then we get transitive relations. Now definition. So there are several items in the definition. First, that two convex orders are equivalent, so they are on PD minus 1 of G are equivalent if each d-Cartège P has the same type PD, yeah. Has the same type type with respect to this both order. So every d-Cartège is equally ordered. And for convex order, for a convex order and pair of d minus 1, so it's convex order here. So I just consider here. And a pair of d minus 1 Cartèges on G. P is stably precedes Q, and we write it P with dot Q if for any convex order which is different from our, we have the same relation for this pair. So that if P less than Q, and for any convex order, yeah, particularly this one, we have the same relation between these two Cartèges. And d-Cartège 1, 2, 3, a d-Cartège P in PD is standard no, it's dense, and it is of standard or anti-standard type. So if the corresponding sequence for the standard we have.
Oh, sorry, Gleb, I just understand. You can replace order by opposite order, yeah? Always.
Yeah. So if we have.
But then if this constraint has no sense because you can take order prime opposite to P less than Q.
No, this is not true. So we can because you have inverse on only on d-Cartèges. So it's not on pairs. So therefore, it just on Cartèges you can inverse, but for element, it's not necessary. So they would be inverted. And it is dense. So if it's standard, then the corresponding sequence we have for any I. So there is no R such that for some I we can find Si plus 1P, which is stably less than R, and this is stably less than I of P. And for anti-standard, it would be vice versa, so that we can find some path which is d minus 1 Cartège, which is less than Si plus 1 of P. So that means so dense means that we cannot insert some Cartège between them with respect to some order.
Is it true that in definition 2,
Yeah.
I should read for any convex order as for any equivalent convex order?
Yes. Yeah, thank you. Yes. Yes.
10 minutes diagram.
Okay, just 10 minutes, good. So the fifth point of the definition, so a rising flip in a convex order at a dense standard D-Cartège do the following. So we just in this D-Cartège, so we reverse, so we make it, send it from standard to anti-standard. So that means that yeah, so we just consider such D-Cartège, consider the sequence, and then if it's it's dense, then we can reverse order, and from anti-standard it would be a lowering, and lowering flip. If we do this, if in anti-standard we reverse order. And then easy observation that flip, so if we have convex order, it make a flip, then it's send convex order to a convex order. And the rising flip diminish the number of standard standard Cartèges by 1, and lowering increases. So now we define directed graph OD of G, so whose vertices are equivalent classes of convex orders on PD minus 1 of G, and whose edges are pairs sigma sigma prime, such that sigma prime is obtained such that some of representatives of this class, it's sigma, is obtained by rising flip from some representative of sigma prime, but in fact, so it is then any representative is obtained because of this density condition. And now So theorem 1. So this graph is acyclic, ranked graph with one source. It's standard convex order and one sink. So it's anti-standard. Then theorem 2. So each maximal chain of convex orders in this graph determine a convex order on PD determines a convex order on PD of G. And theorem 3 is converse to this theorem, namely that any convex order on PD of G can be represented as a maximal chain. So now I will define this map.
By maximal chain and an order in PD-1.
What? In the maximal chain in order? Yeah. In or in maximal chain in or D minus 1 of G. Yeah, thank you. Yeah, so now we define this element. So we just now what would be NGD? So it is just 1 second. It is NGD. So we have just 1 second. So we started. Yeah, okay. So then NGD is so we consider NG. So we consider V tensor power in N. So we consider D simplex equations on NG. So here D minus 1. And this is this number, but we have considered the number of D minus 1 Cartesians.
So you consider graph to have n is finite. Yeah, so graph has no infinite.
Initial graph.
Yeah.
So it has loop, but not oriented.
It has no oriented loops.
No oriented loops.
So NGD will be finite.
Finite, yes. So it would be finite.
Is it possible 5 minutes or?
Yes, I just finish in 1 minute. So just only. So we have this tensor product. So we have now we take standard order. So we have element. We take element standard element in. So then we have sync. We take sync in OD of G, and we consider source. Vice versa, source and sync in OD. Then we consider maximal chain, so 0. Some number K. So we have maximal chain, and then so we have so 0 is just order on OD. So therefore we just consider so element number of elements. It's exactly it is defined on D minus 1 Cartesians. So we consider tensor product in this cardinality n minus G of D minus 1. But now we take them names. So that means that we consider not arbitrary, but how we will put 1, 2, 3, 4, so on, because of this order. So we have for each D minus 1 Cartège, so we have its own element, and then we have this order with respect to standard order. So therefore, it's just this tensor product, but with names. So therefore, this V is just first D minus 1 Cartège with respect to standard order, the next one, and so. So we just consider such a tensor product, and then we found we look for a dense family. So it would be D element of D minus 1 Cartèges, and then we apply operator A at dense tensor product of V, which correspond to the dense standard D Cartège. And then we apply this R to this element, and then we continue follow to this chain, and then theorem that result of this application due to this chain, it doesn't depend on the chain, on choice of the chain. The result on a choice of a chain, of a maximal chain. And so we get such this element. Okay, so thank you for attention.
Questions?
Could you mention an application of this stuff?
So this is application of Manin-Schechtman orders to graphs. Yeah, so therefore for graph you can construct. Yeah, so it is. So I just have to mention. So we have no. So they started from symmetric groups. So we have no symmetric. So we have no analog of symmetric. We started in their language so from the second order. So therefore we started here from first. It would be tetrahedron equation of Zamolodchikov. So we have no Young-Baxter theory for this. So we have to start it from the three-dimensional. So we have no theory for Young-Baxter at this moment, at this point.
Yes.
Is it true that an application of this law is that through theorem 2 you can cook new R matrices for D plus 1 simplex equations? No? So I should not interpret this a way of constructing bigger D simplex equations with D plus 1, given that you have one with D and a graph.
Maybe
No.
you can explain me. It's a break. I can't answer your question.
Okay.
Can one
Sorry,
think
please.
of this D-simplex relation obeyed by R as a sort of flatness condition in this context?
So, I don't know. Maybe you else explain me. Mark?
Yes. Oh, sorry. Yes.
So thank you for the nice. I understand that my Voronowicz teach me that the Young-Baxter equation is just nothing else like Breit or Artin relation coming. Yeah. So and that we of course can extend it in the any Coxeter group or an Artin group the relation, but this is only by root system. But here you have like multidimensional situation. So my question is, if you have under this some exam coming from groups.
So this, so Manin-Schechtman, so they consider higher braid groups related, but their theory is just for line graph. So if you consider, yes, so maybe I forgot to say, so if you consider G as a line graph, then you get this higher Bruhat order due to Manin-Schechtman. And yeah, but here, I don't know. So
But this is more general.
yeah, so it's just that we want to construct something related to the graph. So the graph, we have solution to simplex equation, and then we construct some elements or some transformations. And so just maybe why it's dt. So if we consider exactly this line graph and consider simplex, so this is Lustig solution, which probably disappears, then it would be dt transformation for SLN, for cluster algebra for Bruhat cell on Gmod U.
Any other remarks or questions? So it's time to thank the speakers.
Thank you.